Hello everyone, welcome to my channel. Please subscribe my channel and like, comment and share the videos. Today we will see about the solution of linear non-homogeneous recurrence relation with constant coefficient. So before going to see how to find the solution, let's define the linear non-homogeneous recurrence relation. So linear degree k non-homogeneous recurrence relation is of the form like this one, which is of the form like this one. You see this, which is a non-linear, and linear. You can see that Fn is different from 0, where the coefficients C1, C2, Cn are constants. That's why we call it a constant coefficient in linear non-homogeneous recurrence relation. So from this general definition, we can adapt the second order linear non-homogeneous recurrence relation with constant coefficient. So a non-homogeneous second order linear recurrence relation with constant coefficient is of the form this one, where the coefficient C1 and C2 are constants and Fn is different from 0. Examples of non-linear non-homogeneous recurrence relations are an minus 3an minus 1 plus 2an minus 2, which is equal to n squared plus 1. You can see that the coefficients are constants and there is no product or power on that numeric terms of the recurrence relation, so it is linear. And since the function Fn is different from 0, so it's non-homogeneous. Similarly, an minus 1 minus 6, an minus 2, which is equal to the power of n, is also another type of non-homogeneous linear recurrence relation. And the third example is an minus 3, an minus 1, which is equal to n times 3 the power of n, is also another non-homogeneous linear recurrence relation with constant coefficient, but this one, the degree of this example of non-linear recurrence relation is 1, and the other 2 are the degree of the recurrence relation is 2. Now, when we see this theorem, if ANP is a particular solution to the linear non-homogeneous recurrence relation with constant coefficient, then every solution of the form an is equal to an h plus anp is a general solution to the linear non-homogeneous recurrence relation with constant coefficient, where the an part, the nh part, is the solution of the associated linear homogeneous recurrence relation. So to find the solution of the non-homogeneous recurrence relation, we use the method of undetermined coefficient. The method of undetermined coefficient uses a guess solution to the particular solution of the non-homogeneous recurrence relation and determine the coefficients, the values of the coefficients in the general expression of the solution. So the trial solution or the initial guess to find the solution of the non-homogeneous recurrence relation depends on the functions that makes the recurrence relation non-homogeneous. So for instance, in the examples here, the functions that makes the recurrence relation non-homogeneous is polynomial function. On the second example, it is an exponential function. The other one is the product of polynomial and the exponential function. So depending on the functions that makes the recurrence relation non-homogeneous, we can give an initial guess or try a solution to the recurrence relation. So when Fn is an exponential function, which means Fn is d times n in base a, there are two cases. If a is not the root of the characteristic equation to the homogeneous part, then the particular solution, the initial guess, will be taken as n will be c times a, the power of n will be taken as this one. If a is a root to the characteristic equation to the homogeneous part with multiplicity m, then the initial guess will be taken as c times n the power of m times n in base a, where n the power of m is the multiplicity of the root a, the multiplicity of the root a. And the other one is when the function fn is a polynomial function in the form like this one. If it is of the form like this one, then it has two cases. If one is a root of the characteristic equation to the homogeneous part, then the initial guess will be taken as C0 plus C1n plus C2n squared plus ck n the power of k. If one is a root, this one is when one is not the root. If one is a root to the characteristic equation to the homogeneous part with multiplicity n, then the initial guess or the trial solution to the to find the particular solution will be taken as C0 plus C1n plus C2n squared plus ckn squared times n the power of n the power of m. And the third case is when fn is a product of exponential and polynomial function. So we have the two cases similarly. If one is not the root of the polynomial, the characteristic equation to the homogeneous part of the recurrence relation, then this one will be taken as the trial solution to find the particular solution of the non-homogeneous part. And if one is the root of the characteristic equation with multiplicity m, then the particular the trial solution to the recurrence relation will be a0 plus c1n plus c2n squared plus ckn the power of k times n the power of m times n in base a will be taken as this one. So we have seen these three cases. Let's see with an example. Let's see with an example. The first example is find the solution of the recurrence relation given by an is minus 7 an minus 1 plus 10 an minus 2, which is equal to 7 times 3 the power of n. Then you can see that let's do first the homogeneous part by making this one 0. When we are making this one 0, it becomes homogeneous. So what is the characteristic equation to the non-homogeneous, the homogeneous part? So the characteristic equation to the homogeneous part is r squared minus 7r plus 10, which is equal to 0. Now to find the root to this characteristic equation, what are the numbers that their sum is minus 7 and their product is 10. So the numbers are minus 2 and 5. So r minus 2 times r plus 5. So the roots are r is equal to 2 and r is equal to minus 5. Hence, the solution to the homogeneous part. The solution to the homogeneous part is this one. An which is equal to c1 to the power of n plus c2 times minus 5 to the power of n. Now to find the solution to the non-homogeneous part, 7 times 3 is the power of n. So since 7d is 7 and 3 is not the root of the characteristic equation to the homogeneous part, the roots of the homogeneous part are 2 and 5, so that 3 is not the root, so that the trial solution will be c times 3 is the power of n. Now substituting this trial solution to the given non-homogeneous recurrence relation, we have the following: 7 times 3 is the power of n is equal to c times 3 is the power of n minus 7 times c times 3 is the power of n minus 1 plus 10 times c times 3 is the power of n minus 2. Now, taking c times 3 is the power of n minus 2 as common, we obtain 3 square on this one. What remains when we are taking c times 3 is the power of n minus 2 was common. When we are taking this one, what's left here is 3 square, which is 9. And on this one, 3 times 7, which is minus 10 to 2. And what's left here is 10. So adding this one, you will get minus 2 times c times 3 to the power of n minus 2, which is equal to 7 times 3 to the power of n. So cancelling those similar terms, you will get that c C minus 63 over 2. Therefore, the particular solution to the non-homogeneous part, will be this one. Hence, the general solution to the non-homogeneous linear recurrence relation is given by adding the homogeneous part, and the solution to the non-homogeneous part, the solution will be this one. The solution is given by this one. Let's see another example. Find the solution to the recurrence relation given by an minus 4 an minus 1 plus 4 an minus 2, which is equal to the power of n. This one is also similar to the above question. Let's see the characteristic equation to the homogeneous part. Taking the homogeneous by making the non-homogeneous part is equal to 0. The homogeneous part, the characteristic equation is r squared minus 4r plus 4, which is equal to 0. So what are the numbers which their sum is minus 4 and their product is 4 is minus 2 and minus 2. So r minus 2 the whole square, which is equal to 0. So that is a perfect square. R is equal to 2 is the root of the characteristic equation with multiplicity 2. Since the root of the characteristic equation is repeated, so the solution to the homogeneous part, is given by this one. C1 to the power of n plus C2 n times to the power of n will be the solution. Now to find the solution to the non-homogeneous part, you can see that the one which makes the non-homogeneous part the exponential function to the power of n, the base 2 is the root of the characteristic equation to the homogeneous part. So that the trial solution to find the particular solution of the non-homogeneous part is this one. So C times n squared times to the power of n. So substituting this trial solution on the given non-homogeneous recurrence relation, you will obtain this one. C times n squared times 3 to the power of n, and minus 4c times n minus 1 the whole square times 3 to the power of n minus 1 plus 4 times c times n minus 2 the whole square times 3 to the power of n minus 2, which is equal to the power of n. Now, when we expand these terms, you will get the next equation. So c times n squared times 2 to the power of n minus 4, c times n squared minus 2 to the n plus 1 times 2 to the power of n minus 1 plus 4 times c n squared minus 4n plus 4 times 2 to the power of n minus 2, which is equal to the power of n. Now let's take the common term on both sides. So c times 2 to the power of n minus 2 is a common one. So what's left here is 2 to the power of 2, which is 4 times n squared. 4 times n squared is left. What's left here is 2 times 4, which is minus 8 times n squared minus 2n plus 1. And the last one, what's left is 4 times n squared times minus 4n plus 4, which is equal to the power of n. So collecting those like terms, so when you multiply this one and collecting those terms which have the same power, so 4n squared minus 8n squared and 4n squared, you have this one. So and the other one is 4 16n and minus 16n, and the number is minus 8 and 16 plus 16. So this term plus this term is 8 cancelled by this minus 8, and plus 16n is cancelled by plus 16n. So minus 8 plus 16 is positive 8. So that c times 2 to the power of n minus 2 times 8 is equal to the power of n is left. So that rearranging, we get the value of c will be this one. So that the particular solution to the non-homogeneous part will be 1 over 2 times n squared plus 2 to the power of n will be the particular solution. Therefore, the general solution to the given non-homogeneous recurrence relation will be the sum of the solution of the non-homogeneous part plus the sum of the non-homogeneous part, So C1 to the power of n plus C2 times n times to the power of n plus 1 over 2 times n squared times to the power of n will be is the solution of the recurrence relation. Let's take another example with the polynomial function. a polynomial. It makes the non-homogeneous part becomes a polynomial function. So an minus 2, an minus 1 plus an minus 2, which is equal to 5 plus 3 times n. So the characteristic equation to the homogeneous part is r squared minus 2r plus 1, which is equal to 0. So factorizing this one, you'll get r minus 1 the whole square, which is equal to 0. So r is equal to 1 is the root of the characteristic equation with multiplicity 2. Hence, the root of the solution of the homogeneous part will be this one. The solution to the homogeneous part is this one, so which is C1 1 to the power of n plus C2 n times 1 to the power of n. Since 1 to the power of n is 1, so C1 plus C2 times n is the solution to the homogeneous part. Now, to find the solution to the non-homogeneous part, the one is the root of the homogeneous part, so that the trial solution to the non-homogeneous part will be n times n to the power of n times n, which is n squared times n naught plus a1 times n. Since it is a linear function, it becomes the trial solution will also become a linear function, and n squared is obtained because of 1 is the root of the homogeneous part of the root of the homogeneous part. So that substituting this trial solution on the given non-homogeneous recurrence relation, you will obtain this one. So when you are substituting on the an part, n squared times a naught plus a1 n minus 2 times, when we are substituting on the an minus 1 part, 2 times n minus 1 the whole square times a naught plus a1 times n minus 1, and plus substituting on the an minus 2 part, n minus 2 the whole square times a naught plus a1 times a minus 2, a1 times a minus 2. So which is equal to 5 plus 3n. So you have this. So when you are expanding n minus 1 the whole square into n minus 2 the whole square, you will get this one, n squared times a naught plus a1 times n minus 2 times n squared minus n to n plus 1 times a naught plus a1 times n minus 1 plus n squared minus 4n plus 4 times a naught plus a1 times n minus 2, which is equal to 5 plus 3n. This equation satisfies for every values of n. This equation works for every value, so that let's substitute n is equal to 0 and n is equal to 1. N is equal to 1. So when n is equal to 0 is substituted, you will get that you can see that n is equal to, when you are substituting n is equal to 0, this term becomes 0. What's left is 8 minus 2 times a1. This term becomes 0. And minus 2 times a naught plus a1, 0 minus 1 minus a1, and this term becomes 0. 4 times a naught plus minus 2a1. So that rearranging that, you will get that a2 times a naught minus 6a1 is equal to 5 is obtained when you substitute n is equal to 0. When you substitute n is equal to 1, you will get 2a naught is equal to 8. You will get 2a naught is equal to 8. So a naught becomes 4 when you are substituting 4 here, which is becomes 8, and subtracting it from 5, you'll get 6a1 is equal to minus 3. So the dividing by minus 6, you'll get a1 is equal to 1 over 2. So the particular solution to the non-homogeneous part, becomes this one. Hence, the general solution to the given non-homogeneous linear recurrence relation is the sum of the homogeneous part and the non-homogeneous part. So it becomes this one. Okay, the last example is when the non-homogeneous becomes the product of polynomial and exponential function. And we have given two initial conditions to determine the coefficients of the solution to the homogeneous part. So what the equation is? The equation is an minus 6, an minus 1 plus 8, an minus 2. So the characteristic equation to the homogeneous part is r square minus 6r plus 8, which is equal to 0. So what are the numbers where their sum is minus 6 and their product is 8, which is minus 2 and minus 4. So r minus 2 times r minus 4, which is equal to 0. So r is equal to 2 and r is equal to 4 are the root of the characteristic equation. Hence, the solution to the homogeneous part becomes C1 to the power of n plus C2 for the power of n. Now, to find the solution to the non-homogeneous part, you can see that clearly the base for the exponential part is the root of the characteristic equation to the homogeneous part. So that with multiplicity 1, so that the trial solution to the homogeneous part, to the non-homogeneous part, will be this one. The polynomial function is linear, so that a0 plus a1 n is 1 times the product of 4 the power of n times 1 n is the power of 1, which is the multiplicity of 4 is 1. Now substituting this value, this trial solution to the non-homogeneous recurrence relation, substituting on the an part, substituting on the an minus 1 part, and substituting on the an minus 2 part, you will get this one, which is equal to n times 4 the power of n. So taking for the power of n minus 2 from the whole part for the power of n minus 2 as a common, you will get n times a0 plus a1 n times 4 square. What's left here is 4 square when we are taking for the power of n minus 2. And on the next one, 6 times n minus 1 times a0 plus a1 times n minus 1 times 4 the power of 1 is left here. And the last one, 8 times n minus 2 times a0 plus a1 times an minus 2, which is equal to 4 the power of n minus 2, taking the 4 the power of n minus 2 as common, which is 4 n times 4 square is left. So cancelling this one by this one, cancelling the two values, you will get this equation. You will get this equation 16n times n0 plus a1 n minus 24 times n minus 1 times a0 plus a1 times n minus 1 plus 8 times n minus 2 times a0 plus a1 n minus 2, which is equal to 16 n is left. Now, this expression holds for all values of n. So substituting the values of 0 and 1 in particular, you will get two equations. So when you substitute n is equal to 0, you get a0 plus a1, which is equal to 0. When we substitute n is equal to 1, we get a0 plus 3a1 is equal to 2. So solving these equations from the first equation, a0 is equal to how much? a0 is equal to minus a1 so that substituting on this one, minus a1 plus 3a1 is equal to 2, which is 2a1 which is equal to 2. So a1 becomes 1, so a0 becomes minus 1. Hence, the particular solution to the non-homogeneous part becomes this one, this one. N times a0 plus a1 n times 4 the power of n, which is n times a0 is minus 1 plus a1 is 1, so n times n minus 1 plus n times 4 the power of n, which is n times minus 1 times 4 the power of n is a particular solution. Hence, the solution to the solution to the given non-homogeneous linear recurrence relation is the sum of the homogeneous part plus the non-homogeneous part. So which is C1 to the power of n plus C2 for the power of n plus n minus 1 for the power of n is the general solution to the linear non-homogeneous recurrence relation. But it is given two initial conditions to find the coefficients of the homogeneous part. So when you substitute n is equal to 0, it is 8. So C1 plus C2 is equal to 8. And when you substitute n is equal to 1, you will get 4 times C1 plus C2, which is equal to 22. So solving these two equations simultaneously, or substitute from this equation, we obtain that C1 is 8 minus 2. So substituting this one on the second equation, and here on this equation, you will get 4 times 8 minus 2 plus 2C2, which is equal to 22, which implies 4 times 8 is 32, minus 4c2 plus 2c2, which is minus 2c2, which is equal to 22. So c2 becomes 5. And substituting the value of c2 on the other equation, we will get c1 is equal to 3. Hence, the solution to the given non-homogeneous recurrence relation is an is equal to 3 times 2 to the power of n plus 5 times 4 the power of n plus n minus 1 times 4 to the power of n is a particular solution to the non-homogeneous recurrence relation.